guys, we're going to look at more integrals today. So a lot of it's about being able to pick out the formula that you need to use, recognizing it, and then applying. So first one, we've got the integral of 2 to the power of x plus 3 to the power of x. We know that we can do each of these terms separately, but recognizing the fact that we have a formula that we just follow. A is our numerical base. So in this first one, we have a numerical base of 2. We're just going to follow exactly what this says. So a to the power of x, so we've got 2 to the power of x over natural log of a, which would be 2. Plus, we move on to the next term right beside it, same thing, a to the power of x, so 3 to the power of x over natural log of a, which the base is 3. And then, because it's an indefinite integral, we've got our plus c, that constant that is potentially there. Next one, we've got x to the power of 5 plus 5 to the power of x. Now, these are different things. The first one, super simple, just our power rule. So add 1 and divide. So we add 1, and our new power is power of 6. Divide, and we've got divided by 6, or you can do your times 1, 6, either way, doesn't matter to me. And then this is the new one we just looked at. So a numerical base to the power of x would go 5 to the power of x over natural log of 5, and of course, don't forget your plus c for that indefinite integral. Next one is a little bit more hidden. We have 2 to the power of x plus 4 to the power of x plus 1, all divided by 2 to the power of x. Now here, I can do a little bit of simplifying to make my life easier. Each of these can be divided by 2 to the power of x. If I do a little bit of manipulation on the numerator, we've got 2 to the power of x plus 2 times, nope, what am I saying? Okay, so this middle term, 4 to the power of x, can be rewritten as 2 squared, that same thing as 4, and then we still have our x with that power as well. And then the 1 we're just going to leave as a 1, and everything's going to be divided by 2 to the power of x. Now, all of this now looks very, very easy to simplify if we divide each one by 2 to the power of x. So 2 to the power of x divided by 2 to the power of x is just 1. Plus, here, if we subtract our exponents, we end up with just 2 to the power of x. And then we have 1 over 2 to the power of x, which you can leave it like that, or you can rewrite it as 2 to the power of negative x. So this has a much easier method of being integrated. So integral of 1 is just x. This 2 to the power of x right here follows our formula that we've been using, so 2 to the power of x over natural log of 2. This one, same formula, but we've got a chain rule that's happening with this negative x. The power of, or the derivative of negative x is negative 1, so that actually makes a negative 2 to the power of negative x over natural log of 2. And then we've got our plus c that needs to follow along. And then we really don't want to keep our powers negative, so we're going to simplify that a little bit. I'll come up here and write it. So x plus 2 to the power of x over natural log of 2 minus 1 over 2 to the power of x, when that drops down because of the negative exponent, natural log of 2 plus our c. So that would look a little bit better. Not much, but a little. On the back, we have a lot more that are going to go with our formulas of the arctan and arcsine. It's now just down to us recognizing them. So let's write those up here at the top. There we go. So now I don't have to flip back and forth. We've just got the formulas up here. So noticing what is our a inside of our something squared plus x squared, or the something squared minus x squared, and then square root. And then there's some manipulations that will end up happening as well. So this first one obviously goes with our arctangent. Our a squared is that 1, so our a is just 1. So that one makes it pretty easy just to simplify. 1 over 1 is just 1, so we would end up with arctangent of x over 1, which is just x, so let's just write that as an x, and then plus c. Next one, the number in my a squared position is 4, so a squared is 4, so that means my a is 2. Again, this is the arctangent. It matches almost perfectly. So 4 squared plus x squared on the denominator. We've got 1 over our a, which we just found was 2. Arctangent, whoops, there's a c in there. X over 2, our a value, plus the c. Next one, a little messier. We can make the 5 come out into the front so it looks a little closer to what we're used to with our arctangents. The only problem is this 13 is not a nice, pretty, perfect square, but we can still work with it just like we have been. a squared is 13, so that means our a is the square root of 13. It doesn't look super pretty, but is what it is. So we've got 5 times 1 over a, so I'm just going to go ahead and call that 5 over root 13. Arctangent x over a, which is the square root of 13, plus the c. So it looks a little nastier, but not really any more difficult. On D, again, this is going to be a arctangent, but we have a little bit of manipulation to do. Okay, so in this one, the numerator has the 5. I want it to be a 1, so I'm going to factor that out. So then the denominator, I notice that this is not x squared, and it is 4x squared. So what I'm going to do is I'm also going to factor out a 4. So my denominator is going to have a factor of 4 factored out. So my numerator is now just 1. 9 divided by 4 is this first term, plus, if I factor out the 4 there, we're just with x squared, which is what I wanted. So now this is a little bit closer. Again, the a squared is not super pretty, but easy to take the square root of. That would just be 3 over 2. And now we just substitute things in. So we have to remember that we need to multiply by 5/4. So I'm going to hold on to that for a second. We need to do 1 over a. So 1 over 3/2 is actually the reciprocal of this, so it's really 2/3. Arctangent of x over a, which would be x divided by 3/2. So we'll fix that in a minute since we have some simplifying to do as well. And then our plus c at the end. So fractions, multiply the numerators and the denominators if you'd like, but I also see that 2 and 4 can simplify to 1 and 2. So I'm going to simplify before I multiply, so that would be 5 over 6, arctangent. Here I'm going to multiply by the reciprocal, so this is 2/3 x that we're taking the arctangent of, and then we have our plus c. So that one looks nice and pretty now. Next ones obviously follow the arc signs. They have the square roots in the bottom with something minus something squared. The easy ones at the beginning just follow the formula. Okay, so I've rewritten this here so we can just follow along. So obviously my a squared is 1 on this one, so square root of 1 is just 1, so our a is 1 on this one. So noticing that this is the arc sign, we just follow the formula. So the integral of this, we've got arc sine of x over a. Well, my a is just 1, so that would just be x, and then plus c. So that one was super simple. Next one, also notice that it was an arc sine. This time my a squared is 4, so my a is 2. Just substitute it in. So arc sine x over our a value, which is 2, and then plus c. Easy. Next one's a lot like what we did a second ago. I'm going to factor out the 5, and that leaves me with the 1 over square root 13 minus x squared dx, which is nicer. Again, my a squared is 13, not super nice, so we've got square root of 13 as my a. Multiplying everything by 5, don't forget about that. We've got 5 times arc sine x over a, so we're going to go x over root 13 plus the c. Now h is going to take a little bit more effort. The 5 in the numerator is coming out to the front. I need this to be x squared here, so I'm going to factor out a 4. So before I write what this denominator is right here, I want to write my square root of, I'm going to factor out a 4. So I am bringing a 4 out, which means I've had to divide it from the 9. I've had to divide it from this one right here. So if we think about factoring out a 4, that's a square root. So really what comes all the way out here is going to be a 2. So this is 5 over 2 times the integral of 1 over square root of 9 over 4 minus x squared. Now, if that didn't make sense, maybe pause and think about it for a second and maybe re-listen, or we can talk about it in class. Here my a squared is 9 over 4. Again, easy to take the square root, 3 over 2. Then just substitute into the formula. So 5 over 2 times my arc sine of x over a. So multiply by that reciprocal, 2/3 x, and then plus c. Okay, I'm going to do one more example, a couple more derivatives and antiderivatives to look at, really antiderivatives. So we've got the antiderivative of secant squared x is tangent x, and then cosecant squared x is cotangent, or negative cotangent x. So applying these, we, we'll look at A, B, and C. So A doesn't really play nice with either of these right here. So I'm going to rewrite tangent as a more familiar form, or a familiar form. This is the same thing as sine of x over cosine of x. Now I'm going to use u substitution to do this one, and I'm going to pick my denominator as my u. So my u would be cosine of x, which means du is going to be negative sine x dx. Now if I do that, we end up with an integral, if I do substitution, of negative integral of 1 over u du. So a little bit of substitution gets us into our form of 1 over u, which we know the antiderivative of that is natural log. So we've got negative natural log of u. I'm going to go ahead and sub u back in, so cosine of x, and then we've got plus c there. So that one didn't use those formulas up above, but the next one can get there if we think about our Pythagorean identities. So tangent squared has a Pythagorean identity that we know. So secant squared x equals tangent squared x plus 1. If we subtract that 1, we can rewrite this integral as secant squared x minus 1 dx. And then that can follow what we have up above. So the antiderivative of secant squared x is just back to tangent. Antiderivative of 1 is x. So we've got negative x, and then we put our plus c because it's a indefinite integral. Tangent cubed, very, very similar. So I want you to pause and try that one and see if you can manipulate it based on kind of what we did on B. Okay, on C, this is what you should have gotten to. If not, we'll look at it together in class. Example 4, I'm not going to do, but I am going to give you a couple of hints if you want to go ahead and try. So these are just some different methods that we're going to use to get into some forms that our formula can help us with. So on A, if you think about partial fractions, that would help. On B, if you think about perfect square trinomials, that might help you out there. On C, if we think about vertex form, actually D, vertex form would help as well. So those are hints on example 4. Go ahead and try them, and we'll look at them together in class.